Thank you. Hello, everyone. I'm very grateful to the organizers for inviting me to participate in this program and to give a talk. The last time I visited Erwin Schrödinger Institute was March 2000. It was another program. If I remember, it was program on string theory, and I gave talk on supersymmetric duality rotations. And today's talk is again about duality rotations, but in conformal high-speed models. So talk is based on two recent works. One I wrote in June, and the other joint work with Emanuel Raptakis, who is my PhD student. So the early work is mostly devoted to supersymmetric field theories, and I will use only an appendix from that paper devoted to bosonic models. The paper with Emmanuel, it discusses both non-supersymmetric and supersymmetric duality-invariant high-speed models. And so my talk will be about non-supersymmetric models. Supersymmetric story requires some prerequisites. I decided not to discuss supersymmetric duality-invariant models. So first of all, what this talk is about. It is about U1 duality invariance in Fradkin-Zeitlin models for conformal high-speed fields, and their nonlinear and linearized versions. Duality invariance is understood in my talk as continuous symmetry of equations of motion. So as you know, there exist different approaches to duality, in particular, duality as manifest symmetry of the action. This approach was advocated, for example, by Bunster and Mark Renault. And many colleagues in this audience have worked on various aspects of duality, and I apologize for not being able to discuss their work. This topic is huge, and separate talk or several talks would be required to review different approaches. So, however, I'd like to mention old work by Fradkin and Zeitlin, which I studied when I was PhD student, quantum equivalence of dual field theories, and also very recent work by Avetisian, Evnin, and Karapet Makropchan. I think Karapet will discuss this work in next week or week after. So this is a brief plan of my talk. So I start with electromagnetic duality. I talk about U1 duality in nonlinear electrodynamics, and then I briefly discuss conformal duality invariant electrodynamics discovered last year. Then I say a few words about conformal geometry in d dimensions, d greater than 3, the way supergravity practitioners do it. I mean, just nowadays, I mean, conformal geometry. And then I turn to duality invariant conformal high-speed models, and at the end of my talk, if time permits, I'd like to discuss your duality for complex conformal high-speed fields. So let me start with electromagnetic duality. You all know that concept. It's ancient concept in Maxwell. Electrodynamics is the simplest and oldest example of duality invariant theory in 4 dimensions. So this is just famous Maxwell-Lagrangian, and so field strengths F are based Bianchi identity. Bianchi identity this, and Bianchi identity is that, and the equation of motion is this, and you can see that the equations of motion and Bianchi identities have the same functional form. Therefore, one can consider duality rotations. So, well, F plus I F tilde is Hodge dual, changes by phase factor. Such transformation mixes electric and magnetic fields, and Maxwell-Lagrangian changes under duality rotation, but the energy momentum tensor is invariant. So this property also holds in U1 duality invariant nonlinear electrodynamics. So Maxwell theory is a linear theory, and in 1934, Borninfield put forward a particular model for nonlinear electrodynamics. It's famous Borninfield theory, involving square root of minus determinant of eta plus GF. G is coupling constant. So they considered it as, Borninfield considered the theory as new fundamental theory of electromagnetic field. In 1935, Schrödinger showed that Borninfield theory possessed invariance under generalized U1 duality rotation. So unlike Maxwell theory, this is nonlinear theory, but U1 duality was still there. And the way Schrödinger did it, he reformulated Borninfield theory in such a way that there was manifest U1 duality invariance. I think at that time he was based at Oxford. He escaped from Nazi Germany. So a year or two later, he returned to Austria. Then he came back to the island. He spent 15 years in Dublin, where he wrote in the 40s several more papers on nonlinear electrodynamics. In particular, he showed, he found very interesting plane wave solutions in nonlinear electrodynamics. So he was very, very enthusiastic about Borninfield theory. So, we know that the original expectations of Borninfield never came true, and Borninfield action, so that, the theory is thought fundamental theory of electromagnetic field, but it repeated again in spotlight in the 80s when Fralkin and Zeitlin showed that Borninfield action appears as low energy effective action in string theory. Renewed interest in electromagnetic duality emerged in the 70s with discovery of supergravity. So people observed interesting patterns of duality in extended supergravity. It's Ferrara, Scherk, Zumina, Kremer, Julia. And soon there was developed general theory of duality invariance in 4 dimensions. There was fundamental work by Gaillard-Zumina, 81. Then there was pause, some 14 years, and then Gibbons, Rashid, essentially after work by Zeitlin, I think on D3 brane actions in, Gibbons, Rashid, Gaillard-Zumina developed general theory of duality invariance in 4 dimensions. So that theory was extended to higher dimensions. Again, Gibbons, Rashid, Raki, Tani, Aschieri, Brace, Marario, and Zumina. And there was also developed a general theory of duality invariance in supersymmetric nonlinear electrodynamics, n equals 1 and n equals 2. So with Stefan Tyson, we wrote 2 papers in year 2000. And so the first paper was presented at Erwin Schrödinger Institute in March 2000, talk I mentioned. A year later, there was another important development. Ivanov and Zupnik derived interesting reformulation of duality invariant nonlinear electrodynamics with manifest duality invariant self-interaction. And that reformulation allows one to generate duality invariant solutions. So just a few words about nonlinear electrodynamics. Duality invariance in nonlinear electrodynamics. So in general, nonlinear electrodynamics is described by Lagrangian, which is just nonlinear function of field strength. So, well, here I don't consider high derivative K, well, just presence of high derivatives. So now, using this definition of new object G, in terms of which the equations of motion are defined. So, we have two sets of equations: Bianchi identity and so the equations of motion. So again, they have the same functional form, but not, G tilde is not just, it's nonlinear function. And because they have the same functional form, we can consider so-called duality transformations. So with involving some non-singular matrix from 2 by 2 matrix, and so G prime F prime is by definition must be functional derivative, just partial derivative of some Lagrange L prime, and that Lagrangian always exists. And the story becomes non-trivial if L prime coincides with L. So in such a case, we say that nonlinear electrodynamics is duality invariant or self-dual. And then it can be shown that only one duality rotations transformations can be consistently defined in nonlinear case. So the matrix A, B, C, D is just element of SO2. And in the case of Maxwell theory, we can also have scale transformations. But I mean, they rule out if we require the NG momentum tensor to be duality invariant. So second condition that follows from this fundamental equation is that Lagrangian must be solution of so-called self-duality equation. So with Stefan Tyson, we call it self-duality equation. People use different names. Renata Kalash likes name Noter, Gaillard-Zumina. There are different names in the literature. So now this self-duality equation involves field strengths and the equation of L and G. So essentially, G tilde plus F tilde is 0. This is self-duality equation, and this is equation on Lagrangian. Every solution of this equation is defines U1 duality invariant field. So the equation was first derived by Gibbons-Rashid, and soon Gaillard and Zumina showed that this equation was trivial implications of their 1981 paper. And unfortunately, that paper, they didn't consider, they restrict the analysis to quadratic Lagrangian in the field strengths. They took complete care of matter couplings, like couplings to dilaton and axial, no, to G over H sigma models, but they didn't consider the case of nonlinear electrodynamics. So U1 duality invariant theories or self-dual models for electrodynamics possess several remarkable properties. NG momentum tensor is always duality invariant. In the presence of dilaton and axion, U1 duality can be extended to non-compact duality SL to R. And so the last property, remarkable property, there is self-duality under Legendre transformation. So in the case of nonlinear electrodynamics, just Legendre transformation is defined in standard way. So we replace Lagrangian LF by new Lagrangian. We introduce auxiliary field. We replace F by unconstrained field, and we introduce Lagrange multiplier, dual field strengths. When we vary Lagrange with respect to dual for potential, well, LF becomes a solution of Bianchi identity, and then we return back to the original theory. But on the other hand, we can eliminate F, which is unconstrained field here, using its algebraic equation of motion, and as a result, we end up with a model involving only dual field strengths. It's dual theory. And so this dual theory is familiar to everyone from Zyberg-Witten theory. And in the case of Ivan duality theory, so if Lagrangian L of F solves the duality equation, then dual Lagrangian coincides with the original. So that's why we, people sometimes speak of self-dual electrodynamics. Now, say from the point of view of supersymmetric extensions, it is useful to recast Lagrangian, which is scalar field of, Lagrangian scalar function of electromagnetic field strengths in terms of two invariants of the electromagnetic field, alpha and beta. These invariants can be packaged into complex variable omega, and then the Lagrangian can be written in this form. And then the self-duality equation becomes equivalent to an equation on this coupling lambda. And if we assume that lambda is real analytic, then the general solution can be written, general solution of self-duality equation can be written as Taylor series. So involving constant coefficients CPQ. And then it can be shown that all coefficients with P not equal Q are determined in terms of diagonal coefficients, CR, R. And those remain undetermined. So self-duality equation, general solution of self-duality involves an arbitrary real function of one real argument. Now, so far I discussed theories, nonlinear electrodynamics without high derivatives. What happens if we consider models with high derivatives? Well, modification is very simple. So we have to replace partial derivative, just in definition of G tilde, by functional derivative, and self-duality equation should be replaced by integral equation. And in that equation, G must be, so the action S of F must be considered as function of unconstrained to form. So this equation must hold for just arbitrary F. And when with Stefan Tyson, we just thought about just high derivative generalization, because in supersymmetric theories, there are all these high derivatives floating around. And works by Aschieri, Ferrara, Zumina, and Kalash and collaborators, motivations were different. So Kalash and collaborators, they considered Borninfield actions with high derivatives. Now, as I mentioned, in the year 2001, Ivanov and Zupnik proposed a reformulation of nonlinear electrodynamics. So what was rational for that? I mean, Ivan duality theories are solutions of self-duality equation. And this equation is nonlinear, and Ivan duality-invariant deformations of Lagrangian are difficult to control if you just consider deformation as just solution of that equation. And what Ivanov and Zupnik did, they propose reformulation of nonlinear electrodynamics with the property that Ivan duality invariance becomes equivalent to manifest Ivan duality invariance of the interaction. So the the way the reformulation occurred is very interesting. They actually studied N=3 Borninfield supersymmetric Borninfield action in harmonic superspace, and just it was byproduct of, they look at the component structure of that Borninfield action, and there was auxiliary field that they thought it was not accidental, and they found a good application of that auxiliary field. And so 10 years later, other people, Bassart, Nikolai, Karasko, Kalish, Roiban, they had completely different motivation. They look for, they tried to understand structure of counterterms and extended supergravity theories. And they believe that self-duality, duality invariance may be just may allow the requirement of duality invariance may allow to reduce the freedom in choice of counterterms. They put forward a so-called twisted self-duality constraint. And then constraint turned out to be just a variant of the Ivanov-Zubnik formulation. So I should say a few words about Ivanov-Zubnik formulation. So it involves an auxiliary antisymmetric tensor VAB. And so since it's four-dimensional story, antisymmetric, well, to form is equivalently described by symmetric rank 2 spinor VAB and its conjugate. Now, their reformulation, well, they just replaced the original Lagrangian L of f with the new Lagrangian involving well, auxiliary variable V is unconstrained field. So there is quadratic part and there is interaction. So interaction depends on V only. And so the field V can, well, just appears in the action in Lagrangian without derivatives, and therefore it can be integrated out. So when we integrate V out, we end up with the original field. And then they showed that in terms of the condition of U1 duality invariance in the original theory is equivalent to manifest V1 invariance of the interaction. So, okay, because, well, interaction involved depends on V, and V is to form, there are only two invariants you can construct using to form nu and its conjugate, and, well, just, it can be shown that self-duality equation is equivalent to U1 duality, manifest U1 invariance of self-interaction. It means if you choose any function h, which is function of nu bar, and integrate out V, you end up with duality invariant theory. So now, so the talk, my talk is about duality invariant conformal high-spin models. So, well, 21 years ago, Stefan Tyson and I look for models possessing both duality invariance and superconformal symmetry. Essentially, we just we are motivated by conjecture about low energy effective action for n equals 4 SUN supernomial theory on the Coulomb branch. The conjecture state that that action must be duality invariant, and so we look for those n equals 2 duality invariant theories which are superconformal. So we just show, well, we realize that such models exist, but the derivation in closed form was not possible at that time. We found perturbative solution for just to certain order for duality invariant model. So the first line involves, just kinetic term for n equals 2 vector multiplier, and then, well, just integral over full superspace, it depends, well, it's interaction. And interaction is determined by several parameters. The leading term is, well, it's log W bar. So coefficient in that term is, well, according to Dine-Zimberg, is one loop exact. So it's not present in the classical theory, generated only at one loop. And according to conjecture, well, just essentially just about low energy effective action for n equal 4 superamines, the action should be involve low energy action should involve certain parameter. That parameter C is anomaly coefficient n equals 4 superamine theory. In general, we can have n equals 2 superconformal theories, and they involve additional parameters. Like, I mean, here we have extra parameter D, which is not determined by self-duality equation. So, so derivation of that result was difficult. We got tired, and so 21 years ago, we didn't look at simple cases. Non-supersymmetric case, n equals 0, and n equals 1 supersymmetric case. So 20 years later, other people have studied non-supersymmetric case, and they obtain exact solution. So this is work by Bandas, Lechner, Sorokin, and Townsend, published last year, in which they constructed a conformal U1 duality nonlinear electrodynamics. So the Lagrangian involves parameter gamma, so essentially just one parameter deformation of Maxwell theory. So omega is the same complex combination that appeared earlier. Yeah, this is the omega combination of two invariants of the electromagnetic field. So that parameter gamma, they show, is arbitrary from the point of view of duality invariance, but they show that it must be positive to avoid superluminal propagation of electromagnetic field. So now, the same month was work by Kosikov, who basically derived that theory in simple way, but the model was proposed by Bandas, Lechner, Sorokin, and Townsend, and they called it mod max, modified Maxwell theory. So now this model can be obtained in one line using the Ivanovs-Zupnik approach. So in the Ivanovs-Zupnik approach, structure, well, just all information about theory is encoded in interaction, which is some function of nu bar. You remember that nu is well, combination. I'm using two-component spinor notation. Alpha, beta are two-component spinor indices, and alpha dot beta dot just 0,1 half spinors. Well, just if we use Ivanovs-Zupnik approach, then Lagrangian should be function of nu bar. And now, if we require that interaction to be conformally invariant, then there is only one option. So square root of nu bar times some coupling constant. And now, what remains to do is just to integrate out the auxiliary variables v and v bar, and then we end up with exactly the same Lagrangian mod max theory with a parameter gamma related to parameter kappa in this interaction the following way. Now, n equals 1 story very similar to non-supersymmetric case. Well, in June, they appeared two works, and well, all credit goes to the work by Bandas, Lechner, Sorokin, Townsend, in which they just derived this n=1 supersymmetric mod-mark theory. I learned about their work from email or just phone conversation with Dima Sorokin. He mentioned that they found solution, n=1 supersymmetric extension of the theory. And at that time, I was thinking about n=2 story. And I re-derived their solution with, well, I didn't see the result. So, well, first time I did see the result when the paper appeared in the archive, but because the theory is unique, just the same theory I re-derived myself. But I have only one credit. I deserve only one credit. I provided derivation of this model using supersymmetric extension of the Ivanov-Zubnik approach. So this is the last slide concerning supersymmetric theories. As I mentioned at the beginning of my talk, I'm not going to discuss supersymmetric theories, but still I showed you two slides. Now, just let me try to move on to conformal high-spin theories. So let me start with a brief discussion of conformal geometry, the formulation for conformal gravity, introduced by Kako, Townsend, and Van Nieuwenhuizen in the 70s. So well, they realized conformal gravity as the gauge theory of conformal group. So here we have just commutation relations for the conformal group. And so in this setting, we have to deal with conformal covariant derivatives. And beauty of that approach, well, they involve field bind, Lorentz connection. B is dilatation gauge field. F is gauge field for spatial conformal transformations. Beauty of this approach is that covariant derivatives are very simple algebra. So when we impose some constraints, the algebra of covariant derivatives is given in terms of a single object, so-called, well, just famous wild tensor. It is a primary tensor field, dimension 2, and this is the only covariant object in the theory. So if wild tensor vanishes, conformal covariant derivatives commute, become flat, and that property allows one to construct conformal high-spin models in arbitrary conformally flat backgrounds. Now, in what follows, I will often use a notion of primary field. So just primary field is, by definition, is annihilated by spatial conformal generators, and dimension, well, field of dimension del means that it's eigenvector of D, dilatation operator. So in conformal field theory, there is different definition of primary field. It's actually two definitions are equivalent. It's easy to show. Now, it's dilatation gauge field, B can be always gauged away, and then in such a gauge, we have link to tractor calculus. So it's essentially description of conformal geometry used by geometers and many people in higher spin community. Now, well, since I work in 4 dimensions, vector notation is not very useful. So 2-component spinor formalism is by far better. So this is standard dictionary switching from vector notation to 2-component spinor. notation. And now, well, if I have symmetric traceless field H AS carrying AS vector indices, it is equivalently described by symmetric spinor field with S undotted, S dotted indices completely symmetric. Now, the algebra of covariant derivatives that was shown earlier in 4 dimensions is, well, just take this form. And C bar are self-dual and the self-dual parts of the Duality. And the commutation relations, well, the important commutation relations involves K and covariant derivative. So this relation is highly important because this is how we check that some descendants of fields, conformal fields are primary. We have to, primary fields must be annihilated by K. So descendants involve many covariant derivatives of primary field, and we have to move K through covariant derivatives to hit prepotential. So now, now I'm turning to conformal high spin fields. So consider real spin S field in curved space. I haven't yet defined conformal gauge transformations, but so I just introduce primary field in curved space of dimension 2 minus S. And then I can associate with H its descendant involving S derivatives. This descendant, well, it's known in literature as linearized high spin Wild tensor. So it has nice conformal properties. So C is primary, C carries only undotted indices, and it has dimension 2. So since it is primary and dimension 2, the following functional is locally conformally invariant in arbitrary background, arbitrary gravitational background. Now, well, I fixed a dimension of H, and that dimension is compatible with unique transformation law. This is transformation law that corresponds to Fradkin-Zeitlin field. So in Fradkin-Zeitlin approach, they also have traces, but traces can be gauged algebraically, so they just fail. Now, so as I said, C, this field strength was primary in any background, but it is gauge invariant in general background. Well, it's a gauge invariant in generic background only for S equals 1. When S is greater than 1, gauge invariant holds only in conformally flat background. So when background Wild tensor is 0, and in what follows, I will consider only conformally flat background. Now, so we are almost there. Now, suppose I have gauge invariant action functional of of H. Functional action is constructed in terms of C and C bar, linearized Wild tensors, linearized high-spin Wild tensors, and it can be shown that C and C bar obey Bianchi identity for any conformally flat background. So now I can consider just I have to look at the equations of motion, and the equations of motion can be formulated in terms of the field M, which is just derivative, variational derivative of M with respect to C. So I assume that the action can be extended to be a function of unconstrained field C, primary dimension 2 field, and then well, the first variational derivative is also primary of dimension 2. And then it can be shown that the equation of motion is this. It has the same functional form as C. C and M both are primary, they have the same dimension and Bianchi identities, and the equations of motion have the same form. Therefore, we can introduce duality transformations, mixing C and M. So, so we look for transformation, for duality transformation, just continuous duality transformations, and we would like the action, well, our theory to be duality invariant. Means that transform M must be derived from the same action. And then one can get two different expressions for the variation of the action, and comparing them, we are led to, well, higher spin self-duality equation. So any, well, this is equation on the action. Our theory, any solution of this equation gives us a self-dual theory, or duality, one duality invariant theory. In the case of, well, in the spin one case, this equation coincides with Gibbons, Rashid, Gaillard-Zubin self-duality equation. Now, okay, well, as I said, this equation is just an equation on the action of our theory. Do we have solutions? Well, there are two simple solutions. First solution is just Fradkin-Zetlin-Linetsky conformal spin-S action. So in Minkowski space, it was first written by Fradkin-Zetlin in terms of projector, then it was rewritten by Fradkin-Linetsky using in terms of linearized high spin Wald tensors and conformally flat backgrounds. In arbitrary conformally flat backgrounds, we formulated it with Michael Pons. So, but this theory is, well, simple, it's quadratic. Well, we can construct high spin extension of Mott-Marx theory discussed earlier. Here it is. So you can check that this action is a solution, it is an exact solution of a higher spin self-duality equation. It is nonlinear theory. Well, it is conformal, and it is one duality invariant. So, well, essentially, it is one parameter deformation of Fradkin-Zetlin-Linetsky model. For spin one, in the spin one case, it reduces to Mott-Marx electrodynamics. Now, we have two solutions, and then we can ask, well, one could ask another question. Do we have more solutions? And are we able to generate solutions? And in order to generate duality invariant solution, duality invariant higher spin models, it would be good to have formulation with auxiliary variables, like Ivanov-Zupnik type formulation. So, and such a reformulation is not difficult to obtain. So just we can, well, consider a new model involving unconstrained variables eta and eta bar. So eta carries just rank 2s spinor, carries 2s undotted indices. It's primary. It has dimension 2. This these conformal properties coincide with those of the Wald tensor, and we need, well, they must be the same because well, we have c squared, we have eta squared term, we have eta c term. Now, if eta can be integrated out, eta and eta bar, I mean, these auxiliary fields can be integrated out using the equations of motion. And then we are back to the original theory involving C and C bar. What is good about this reformulation is that self-duality equation becomes equivalent to the condition that the interaction is invariant under phase transformations of eta variable. So if we are given such a functional, well, U1 invariant function, then we can integrate out eta and eta bar, and we end up with U1 duality invariant theta. So using that, well, just a new formulation, we can generate new conformal U1 duality invariant models. Say, just here I show that for a spin 2. So, well, just well, the interaction must be scalar, well, scalar, just conformal invariant. So, well, just we look for an action involving just algebraic invariance of eta, and say for, well, well, here they are. Just you can just have a cell of them. For spin 2, there are two invariants: eta squared in eta q. Eta 4 is not independent. And then here, well, here I have an example of U1 invariant self-interaction. So there are two terms, beta and kappa terms. The first term involves eta squared times eta bar squared, what's manifestly U1 invariant. The second term involves eta cube times eta bar cube. So beta and kappa are real coupling constants. Now, well, we can just eliminate the auxiliary fields to end up with conformal U1 duality invariant action. When kappa is non-vanishing, well, it's very difficult to get exact solution, but this is just perturbative solution. So when kappa is 0, we are back to exact solution. Exact solution was this one. Higher spin mod max theta. Okay, so far it was about, the story I told you was about Fradkin-Zeitlin fields, conformal spin S field, a bosonic field involving S undotted, S dotted indices. But say when we consider supersymmetric duality invariant theories, they also involve spinor fields, fermionic gauge prepotentials. And therefore, there should exist a way to define duality transformations for fermions. And more generally, I mean, one can consider complex conformal complex conformal gauge prepotentials with M undotted and dotted indices, M and N different. And so one can define, just introduce gauge transformation for them, just generalizing Fradkin-Zeitlin gauge transformation. So this gauge transformation is conformal provided, well, assuming that phi is primary field, provided, well, just phi has very spatial dimension. Essentially, such fields were such conformal high spin fields were introduced by Misha Vasilyev, and in 2009, they naturally occur as in the component action. Well, they actually originate in supersymmetric superconformal high spin models that we discussed with Monvillian and Tyson a few years ago. And such models were formulated in arbitrary conformally flat backgrounds with, well, in my work with Michael Pons. Now, what do we have in this case? In this case, we have
Sergei, excuse me, just to clarify, these fields, these are analog of partially massless, right?
Why?
Because of higher, do you have higher derivative? No.
No, I mean, just one derivative.
Okay, then I confused, sorry.
No, it's just, It's different Young type. That's basically.
Mixed symmetry.
Mixed symmetry, yeah.
Okay.
I don't use that terminology because I'm two-component person. I'm happy with two-component notation. And I prefer to live in 4 dimensions. So it's mixed symmetry field. Yes, correct. Your question is good because the whole story can be generalized for, can be extended to generalized conformal fields with all derivatives in transformation law. And Emmanuel wanted to include such a generalization in the paper, but I said, well, perhaps it's too much. So what we have in this case, when we have complex conformal fields, we have fields phi, we have fields phi bar. We can construct 2 types of wild tensors with undoubted indices. We also have their conjugates. So we can just, it can be shown that these objects C hat, C check are primary. Here we have their dimensions. And when we take sum of dimensions 4, it means C hat, C check is Lagrangian for, it generates conformal field. So they are gauge invariant in conformally flat background. So here we have 3 gauge invariant conformal high spin action. And now it can be shown that C hat, C check satisfy Bianchi identity. Here it is. And then we can also derive equations of motion. Suppose we have dynamical system with action depending on the high spin wild tensor. So C hat, C check, and their conjugate. And then if we just properly define partial, well, just the first variational derivatives, the equation of motion can be written in this form. And M hat, M check are also primary fields. They have the same dimensions as C hat, C check. And therefore, we can consider duality rotations. So we require theory to be duality invariant. It means M hat, M check must be transformed equations of motion must be generated by the same equation, by the same Lagrangian. And then it can be shown essentially just analysis is very similar to that in nonlinear electrodynamics that the action must satisfy higher spin self-duality equation. So when M and N coincide, we are back to the story considered before. And so far, we have only one solution of this equation, so free conformal high spin action. And as I said, this concept of Ivan duality invariance can be generalized to the case of so-called generalized conformal high spin fields. These cell derivatives in transformation law. There is supersymmetric extension. Actually, there are supersymmetric extensions. We constructed n=1 and n=2 extensions. And I think my time is almost up. Thank you very much.
So thank you very much for the talk. Other questions?
Could you please comment on understanding of this, on how one should understand this symmetry? Because at least in case of spin 1, this duality transformation acts on stress tensor, right? But in terms of, but action depends on gauge potential. So in terms of gauge potential, it is non-local. That's
why?
Then it extends to higher spins.
No. The action is local. In the case of
action is local.
Yeah. All actions are local. All the actions I showed you are local.
I'm not saying they're not local, but the transformation, duality transformation in terms of gauge potential, it acts non-locally or?
Well, at the beginning of my talk, I said that I will consider duality as symmetry of the equations of motion. I didn't discuss duality in terms of potentials. In terms of potentials, you should go back to the work by Teitelbaum, I don't remember. Desert Teitelbaum, then Bunster and No. I mean, they consider duality as symmetry, as manifest symmetry. I discuss duality only as symmetry of the equations of motion.
Okay, thanks. And same stays for high spins. It's just like
that's correct. In principle, for high spins, you can consider duality as manifest symmetry, but we didn't study that.
Yes.
You just said for high spins, you can promote the symmetry to manifest duality invariance at the level of the action. Even in high spins, it's not non-local.
Say again.
So for spin one, let's say at the level of equations of motion, everything is local. But correct. if you want to express it in terms of potentials or make it manifest at the level of action, we get non-local. For high spin,
no.
The non-local operators.
For high spin, the story will be the same as in the case of electrodynamics. So essentially, you just should start from Desert Teitelbaum, Bunster and all, and just go through similar analysis, but for high spin
fields. Sergei, may I ask a question?
Sure.
Vasiliev.
Yeah.
I have first a question and then a comment.
Okay.
Well, the question is that the actions that we have shown for spin 2, they contain this wild tensor and denominator. And my question is whether how much does it make sense to go to flat background in these models?
You mean this action?
Yeah, like this. Yeah.
No, but you see, this is, I mean, this, we have background and in this, just you have excitation. Yeah, I mean, this, it's kind of spontaneously broken conformal symmetry. Here you have to consider just that C cube is non-vanishing, just open domain in the space of fields.
Okay.
Something similar happens in electrodynamics. Actually, nonlinear electrodynamic story is very similar, because when you derive the equations of motion for mod max, then you have to assume that omega is non-vanishing. So the equations are not well defined everywhere. The action is not analytic. That's the point. So if you consider n equal 4 on n equal 4 superior means on Coulomb branch, okay, the theory is defined in terms of n equals to vector multiplied. It's scalar superfield. Well, its field strength is scalar superfield, but on the Coulomb branch, W is nowhere vanishing. Okay, here we have scalar, just scalar develops expectation value. But again, theory is not defined for arbitrary values of fields. Only, you have to restrict, the dynamics is restricted to some open domain. Flat space limit is not defined. Yeah, you're right.
Just maybe a small comment actually on this locality issue that have been mentioned from the previous question. Well, in conformal higher spin theories, there is no issue because scale invariant actually allows one to construct local theories, no problem. In anti-de Sitter, I'm not sure how duality can be defined, and does it make sense actually to talk about this? There, indeed, the locality issue exists and has not been yet analyzed properly, but no matter. I mean, I wonder is there some analog in the ADS hairspins?
No, but you see, well, we can see the completely arbitrary, well, we can see the conformally flat background, arbitrary. For when background is ADS, yeah, we just have action in ADS, but we have to switch from conformal covariant derivatives to Lorentz covariant derivatives. That's it. Yeah. And in the paper we have, in the paper with Emmanuel, we have just some discussion of models in ADS. Yes, you can consider models in ADS. Correct. Yeah.
Okay, thank you.